Okay, this is the GCSE Combined Science Trilogy, Higher Tier, Chemistry Paper 2, 2023. We can see in this first question, it is the combustion of fuels is a source of atmospheric pollutants. Now you need to know certain atmospheric pollutants, but it tells you this whole question is going to be about them, so you need to sort of have in your mind what pollutants do I need to know. Okay, then it says methane is a fuel, balance the equation. Now, balancing equations can be a scary thing for some people. I would always say start with the atom with the most elements, or the molecule rather with the most atoms, and that's our methane. Okay, and that has 5. So if we look at this, this has 1 carbon, and if we look on the other side, there's only 1 carbon. And then this has 4 hydrogens as our methane. And if we look onto this after the arrow, there's only one thing that involves hydrogens, and that is our water, which only has 2. So if we put a large 2 there, that gives us our 4 hydrogens. Now again, before we get to our oxygen or anything else, count how the number of elements has changed. We now have 2 lots of oxygen from our water, and we have 2 lots of oxygen from our carbon dioxide. That makes 4. And if we look on the other side, that means we need to put a large 2 in front to balance our simple equation. Okay, we have this question. Many fuels are mixtures. Petrol and diesel are mixtures of hydrocarbons, and table 1 shows properties of petrol and diesel. We read every line because every line is there for a reason, okay? Then it has this huge table, which we can look at in a second, and then it says compare the properties. Well, compare the properties. Compare means I'm going to be talking about more, less, fewer. I'm going to be using these ER words essentially. And it says properties and then use table 1. Well, what is table 1 about? It tells us just above, table 1 shows the properties. That means we're going to be talking about heading number 1 and we're going to be talking about heading number 2. When we talk about each of those. Now, if we look at comparing the properties, we can then look, we know we're going to talk about 1, we can look at how that is different. Okay, so our first point is petrol has fewer carbon atoms. And again, carbon atoms than diesel. So we're putting both sides of it. We have to say, we're not going to leave it general by saying it or they. That's our number 1 point. We could say petrol has fewer carbon atoms in a hydrogen molecule. We can keep it shorter if we want to. Okay, the next one, we look at these two. Oh look, we can actually say what's different about them. So we can say petrol has a lower boiling point than diesel. And again, we could say petrol has a lower range of boiling points than diesel. The gases released when a fuel is burned in car engines may include oxides of nitrogen, carbon monoxide, water vapor. Which chemical element do all these gases contain? Now, it's only 1 mark, obviously, because it's a multiple choice question, and it says tick 1 box, but it's worthwhile reading all of them and discounting some as we go. So, if we look at carbon, oxides of nitrogen does not involve carbon, so it cannot be that one. Okay, hydrogen, oxides of nitrogen, that also doesn't involve hydrogen. And then it says oxides of nitrogen, okay, so it could be this. Carbon monoxide, well, it can't be that because that doesn't involve nitrogen. That means it must be our oxygen. Okay, we can also look and we know it says oxides and that says oxide. That tells us oxygen is in both. But water vapor, we need to know is H2O to be able to work it out from the oxygen point of view. Where diesel burns in car engines, oxides of nitrogen are produced. Where does this oxygen come from? Now, this is one of these atmospheric pollutants. You need to know where it comes from. And nitrogen comes from the air. Now, this whole topic is actually called the atmosphere, so you can actually just say the atmosphere. You can think atmosphere above, sort of outside in the sky, or we can also think the air that we're breathing in right now. Next question. When diesel burns, particulates may be produced. Now, particulates, again, we're coming back to this at the very start of the question. Did we think about all these different atmospheric pollutants? We've talked about methane in our balancing symbol equation. We've just looked at oxides of nitrogen. We're now looking at particulates. We're going through a lot of these, okay? What environmental effect? Now, environmental means the world around us. It doesn't mean humans individually for me. It means the world around us. And again, from our learning, the only environmental impact or effect that we absolutely need to know is that particulates cause global dimming. Okay, carbon monoxide may be produced when diesel burns. Again, we're talking about all these different atmospheric pollutants. Now we've got carbon monoxide. Give one reason why carbon monoxide is difficult to detect. Well, there are two things you need to know. Either that carbon monoxide is colorless or that it is odorless. It doesn't smell, it doesn't have color. Now, question number 2. Again, we've got this table, so we're going to be looking at this table. They wouldn't give us one if we didn't need to. Explain, and I've put this back in. This is table 1 is actually at the very beginning of the question, but explain why water vapor and not liquid water. If you notice, I'm highlighting all the bold bits. They're the essential bits. Why water vapor and not liquid water is produced when diesel burns. Well, diesel burns, or diesel boils, I should say, at 250 to 350 degrees, okay? So it's a really, really high temperature. Now, what do we know? Well, diesel burns at a really high temperature. And we can say that. We can literally just say, diesel burns at a high temperature. Now, if we really want to be specific, the reason why we've got that table there is for a number is above 100 degrees C. Okay? So what? It's an explain, which means we need to say something and then say because or why. Well, diesel burns at high temperature above 100 degrees. Why is that important? Well, because 100 degrees C is above the boiling point of water. Okay, where it says water vapor and not liquid water, it means we're talking about something above 100 degrees C. Okay? Right, sulfur is a common impurity in diesel. Again, this is our next one. We've talked about nitrogen oxides, we've talked about particulates, we've talked about carbon monoxide. Now we're going to talk about sulfur. And again, the sulfur pollutant is sulfur dioxide. Which it doesn't say in the question. It means we're going to be making sulfur dioxide. But it says explain. Again, explain why this causes environmental. Environmental is the world around us, not necessarily us as sort of humans specifically. So, sulfur dioxide is produced. Okay, we could use a word equation or a symbol equation. In reality, they're not asking for this. They're just asking for what is produced. So, sulfur dioxide is produced, so what? Well, that makes acid rain. Again, so what? Well, acid rain damages lots of things actually. It damages trees, it damages buildings, it also acidifies lakes. Okay, so from your geography, you might know about acid rain. Any of these is acceptable. It's 3 marks, which means they're looking for sulfur dioxide, they're looking for making acid rain, and they're looking for a reason how that damages it. Okay, so you've got sulfur dioxide 1 mark, acid rain 2nd, damages trees 3rd mark. Now next one we've got about chromatography. Totally different question, but again it's used to separate mixtures. Mixtures is really important as a word. We're going to come back to that again and again probably. Chromatography involves a mobile phase and one other phase. Well, what does mobile mean? Mobile means moving, okay? So what is the other phase in chromatography? Well, it's not moving because we just said mobile does that. There's no such phase as recycled phase. Recycling, when we talk about recycling metals or glasses, but not to do with this. And they've already told us, well, they haven't told us, I should say, but viscous phase, we only use the word viscous when we're talking about hydrocarbons and separating crude oil. So it's not viscous. The only one it could be is stationary phase. Okay. Now, why do substances in the mixture separate in the mobile phase? So if you think back to our chromatography, why do these substances separate and create all these different dots if it's a mixture? Well, that's because they have different solubilities. And solubilities, again, is how easily they dissolve in the solvent. So they have different solubilities. We then have how many spots will be produced on the chromatogram of a pure compound. Well, it's pure. We need to look for these words. Pure compound means there is only one compound or one substance inside. And if there's only one, that means it can only be one spot. And we have our last one, our calculation. They haven't given us the equation. We need to know the equation, but crucially, RF value, every single answer is going to be below 1. Okay, that's what is important to know about RF. So if we write our RF equation, or rather, and put the numbers in, it's how far the spot moved, so that's our blue color moved 4.7, divided by how far the solvent moved, which is 5.30. If you notice, I'm not using centimeters, we don't tend to put them in equations. And if we do 4.77 divided by 5.30, we end up with 0.9. And we can check that it's below 1, so therefore it must be correct. Okay, black ink is a mixture of several colors. Plan an experiment using paper chromatography 2. Now, I'm going to circle the plan an experiment, and that's because if they're asking you to plan an experiment, it is something you should have done. It is one of those practicals that you should know. It's not a made-up practical that you'll never have heard of before. Okay, now there's 2 bullet points. The bullet points are essential, and you need to keep going back to those. Separate the colors in black ink. That's our first step. We're going to plan an experiment to separate the colors in black ink and then identify the colors from their RF values. Well, let's put our steps down. What are we going to do? Well, what do we always do? We draw a pencil line when we do chromatography. Draw a pencil line and then put a small dot of black ink. Why black ink? Because it says it in the question. So a small dot of black ink. Okay, that pencil line is really important. Okay, you can say it's near the bottom of the paper as well. Put our small dot of black ink. We then add some solvent. Okay, they haven't given us the solvent in the question. They haven't given us solvent, so we're allowed to just say solvent. Okay, if you said water, that's also acceptable. We then place paper in solvent. But for all those people who have done this practical, you know a really important thing is not below the not above the pencil line. Okay, the rookie error with this one is you just chuck the paper in, and if the pencil line goes into the water or into the solvent, everything's ruined. You start again. So it's making sure we say that bit. What do? We then let it run. We then let it run, and then we mark the solvent front. If you remember, we do that in pencil. We mark solvent front. Okay, now, have we separated the colors in black ink now? Yes. So we can actually tick that first bullet point and go back to it. That's why the bullet points are there. It's to help us, it's to help you work out if you've answered all the points for this question. Okay, so we can almost draw a line under it and say that is how we separate the colors. The next part is how do we identify the colors. Okay, so our next bit is we measure, and again we're going to say equipment, so we measure using a ruler the distance of what? Of all the spots and the solvent. So we're going to measure both of those. Okay, then what do? Well, we calculate the RF value. Why are we calculating RF value? Because in here, in the bullet point, it says calculate RF, or it says RF value. So it's not just see which one has traveled the highest. It's not see if they both travel the same distance. This is RF values. We have to say we're going to calculate it. Our third step, this is the step that a lot of people miss, is we've got our RF value. What do we need to do? We need to compare our RF value with known values. Okay, that's the extra step. Compare RF values with known values. And that, again, is our second bullet point for this big 6 mark question. Okay, it's not a case of we said 6 things, we get 6 marks. It's to get 5 or 6 marks, is it logical? Will we get valid results? And have we said most or all of the steps? Okay, so we've got a pencil line, we've got the dot, everything is in there. Okay, crude oil is a mixture of different compounds. Brand new question. They're talking about crude oil. They've given it in the heading. Everything about this question is going to be about crude oil or mixtures. Okay. Then the next one, give 2 reasons why crude oil is not a formulation. The bold not tells us what they're talking about. So you need to know what a formulation is. A formulation is something that is a useful product that has been mixed in fixed quantities or in measured quantities. Okay, why is crude oil not a formulation? Well, it's not a useful product. Okay, crude oil is not the product that we are. We have to separate it first. So it's not a useful product, and crucially, it's not mixed. Okay, this question is essentially asking you, do you know what a formulation is, and do you know what the opposite of a formulation is? It's not useful, and it's not mixed in measured quantities. So look for in the question those key words and whether you know them or not. That's why we've got all these keyword definitions that you need to know. Describe how crude oil is separated into fractions. This is a describe. Okay, so that is a big part of it, but it's separated into fractions. Again, this is almost like a method. It's not a required practical. So it's not a method it's not a practical you will have done, but it is something you should know. Well, what's the first step? We heat crude oil until it evaporates. Okay, what does evaporate mean? Turns into a gas. I always like to put that in there. Evaporates into gas, just in case they're not sure. I haven't made it clear enough. Okay, now we're going to describe this step. We've heated it, but now we need to describe what happens next. Well, the gas travels into the column. But what is special about this column? Well, the special at the column is it's hottest at the bottom, coolest and it goes cooler as you go up. Okay, it's important to realize then the fractions, again this is fractional distillation, they've used the word fractions in the question. Fractions condense at different heights, okay, going all the way up this column. It's part of it, it's that separating out. And why do they do this? Fractions condense at different heights based on boiling point. Okay, we don't need to say that which one has the highest boiling point, which one has the lowest boiling point. Any specific fractions, it's just generally it's based on their boiling point. Now, the fractions from crude oil contain alkanes. Explain, again, this is an explain, which means you're going to say something and why. Explain why alkanes are cracked. Well, we need to know what cracking is. It's our definition. Cracking, what does that mean? It means making smaller molecules. Okay, it's using heat and pressure to break these large molecules into making smaller molecules. Okay, that's what cracking is. Well, why do we need to do that in the first place? That's what they're asking. Well, there's more useful products. We've just made something new. It's going to be more useful, but also not just the use. Well, because it's more useful, it has a higher demand as well. Either of those two. We need more of these smaller molecules. Now, describe a test. This is great. This is a great question if you know your test. But if we start at the top, an equation for cracking decane is, you don't need to know this equation, which is why they've given it to you in full. Describe a test to identify the gas produced in the reaction. Okay, so gas, you need to know gas, you need to know what produced means. Produced means it's a product. Okay, this is our gas. Now you need to be able to say or describe the test for this gas, which is hydrogen. The test is a lit splint. Okay, you can't really guess this, you have to know this. A lit splint, and what happens to it? It makes a squeaky pop. Okay, it is one of those things you absolutely need to know. Now, alkenes are produced in cracking. The general formula for the homologous series of alkenes is CnH2n, which formula represents an alkene. So we'll come back to this. They've talked about it being a formula, so we're going to be using CnH2n. Okay, if we look at the first one, C2, if they're C2, and we look back to our general formula, it's going to be 2 times 2, which equals 4, okay? Well, that definitely has to be right. This can be correct. That works. C2H6, well, it's got to be 4, so that doesn't work. And we have the bottom one, which is C3. So we need to check that one. C3H, and then it's 2 times 3. Well, that equals 6. So it cannot be the bottom one. It has to be C2H4. Okay, so now this is a big question because you've got the big diagram at the top, but also, and then I've cut it a little bit just to show the method, and this is the method used. Now this is a method, it is a required practical method, you need to know it, but also you need to know the reasons for the steps and how to improve it. So when the question says the method used did not give valid results, that means we did something wrong. So describe one improvement the student could make to obtain valid results. Now, valid results are the ones we actually want at the end. Now, if we go through the steps, they weigh the evaporating basin originally, which is good. They then add the water and weigh it again. So that allows them to work out the mass of water actually in the basin. They then heat the sample for 2 minutes, weigh it again. They then repeat steps 1 to 5 2 more times, and that almost to sort of step 6, that is the one method for that water, and then step 7 is they repeat it with something else, with seawater. Now, how do steps 1 to 5 not give valid results? Well, I don't know if all of the water has evaporated. I don't know if every little bit of water has evaporated. The only way I would know that is if I heat to constant mass. Okay, so a big part of this practical, or sort of improvements to this practical, is knowing that we know the reaction is finished, or we know the practical is finished, the evaporation process is finished when the mass doesn't change, or I've heated it to constant mass. And the next one, we've got this lovely table. It says calculate the value x for the mass of dissolved solids in test 2. Now you can see we've already got the mean, so it's not a mean question. We've got to work out one of the values that we used to calculate the mean. So if we do this from a mathematical point of view, almost sort of as algebra, well, 0.29 equals 0.30 plus x, if we change it, keep it to x, plus 0.26. And if we add all those three together, and divide by 3, that equals 0.29. So all we need to do is solve for x. Now, if we solve for x, we can then have, we times both sides by 3, so we end up having 0.87 equals 0.30 plus x plus 0.26. And again, if we subtract 0.30 and 0.26 from both sides, x equals 0.31. And it's 2 marks because you've had to substitute the values into this sort of formula of sorts, and then you've had to rearrange it to solve for x. Next one is describe a test to confirm that distilled water is pure. To determine purity, there is one way to do this. Well, 2 ways in reality, but for distilled water there is only one. We have to determine the boiling point, because it's only the boiling point and the melting point which will tell you for certain whether that substance is pure or not. So if the boiling point is exactly one temperature, and it's not a range of temperatures, that tells you that that substance is pure. So the test is determine the boiling point, and the result is, well, H2O, the boiling point of water, is exactly 100 degrees Celsius. If it's 102, it tells you it's not pure water. Tap water is potable. Now remember, potable means drinkable. We can drink it without dying, okay? And it's an important part of paper 2 chemistry, especially this environmental aspects of drinking water. A gas is used to sterilize the water, and this is the equation for it is. Now, you should know chlorine is one of the gases used to sterilize water. That's one you need to know anyway. But then it says, what is meant by the symbol? Now, that is something you just have to know. You can't sort of work, you can almost work it out, I suppose, in that there are arrows going forwards and backwards, and that's what a reversible reaction is. The reactions can go forwards and backwards. Again, they show the same equation again. If they want you to use the equation, they will write it again later on in the question if need be. Okay. The reaction is at equilibrium. Equilibrium is important. This is telling us we're now going to be talking about this dynamic equilibrium potentially and Le Chatelier. Okay. And it says the reaction is exothermic. What that means is the forwards reaction is exothermic. And immediately when you get a question like this, if it tells you the reaction is exothermic, you can put this straight onto your equation to show, to remind yourself for the question itself. What happens to the equilibrium position when the temperature is increased? So increased means temperature is going to go up. Okay. Now which one of these arrows is it the top arrow or the bottom arrow which is going to decrease the temperature? Because equilibrium or dynamic equilibrium in Le Chatelier will tell us that if we increase the temperature, the reaction will try and mitigate that increase in temperature and trying to reduce the temperature. So therefore, if we are increasing the temperature, it's going to try and decrease the temperature, which is our endothermic reaction. And again, we've already drawn that arrow to show the direction of the endothermic reaction, and that is going to be the direction that the equilibrium position will move. It will shift to the left-hand side. Okay, now describe a test. There's quite a few tests in this paper to identify the gas used to sterilize water. Well, in that previous bit, they gave you the equation. We know that the test, or the gas, is chlorine, okay? And again, it's one of these you need to know. It's damp litmus paper. Cannot be just dry litmus paper. It's got to have a bit of water in it so that the chlorine will dissolve in the water first to then be able to react with the litmus paper. We have damp litmus paper and it is bleached white. Okay, that is our test. That is the result as well. Not much more else other than you just have to know that. Our next question, another stage in the production is filtering. Well, you should know what filtering means, okay? But this is a slightly different take on it. Explain why potable water contains dissolved solids after filtering. Well, dissolved solids are dissolved in the water, and filtering removes solids. Not dissolved solids, but actual solids. So it's slightly different, okay? They dissolve solids which are suspended in a liquid, like a mixture, whereas dissolved solids are slightly different. How are they different? Well, dissolved solids are very small. That water has dissolved the solid pieces, and it has broken them into tiny little pieces so that these dissolved solids are very small. And because they are very small, again, because is this explained? Because the dissolved solids are very small, they go through the filter paper. Filter paper only filters out those solid particles that will be trapped or that are larger than the filter paper. These dissolved solids are very small, so they go through the filter paper. Okay, an increase in greenhouse gases is causing global warming. Give one effect of global climate change. Now there are endless things you could put here, one of which is not climate change for global warming, but you could have melting ice caps, That's the one that people tend to remember. Melting ice caps, you could have flooding. Okay, again, it's only one. I'm putting two. They're very similar sort of ones though. The next one, explain how greenhouse gases cause global warming. Now, there is more of a physics way, but also this links into physics and chemistry in reality. So we have short wavelength light, and again, this is where that sort of little bit of physics comes in. So short wavelength light, or radiation, and it's electromagnetic radiation, enters the atmosphere. Okay, now you can actually, if you want to, say what it is, and that's UV radiation. Just, it's useful to know UV radiation is that short wavelength light. Okay, it's absorbed, but crucially, this is where it's really, really important. Hold on. It's absorbed and re-emitted. Okay, it's not just absorbed, it's re-emitted as shorter wavelength radiation. Okay, this is the not shorter, as longer wavelength radiation. This is the absolute crucial bit, that you have to have both parts, not just absorbed, not just emitted, it's absorbed then re-emitted as longer wavelength radiation. Again, you can say what type of radiation that is. This is our infrared radiation. You should know that infrared radiation is longer than UV radiation. Okay, now what happens to this infrared radiation? This is absorbed, and it's just absorbed by the atmosphere. Okay, I'm putting it as bullet points because it's these bullet points that will get you the marks. You need to know it's short wavelength radiation that enters the atmosphere. You need to know that's absorbed, then re-emitted as longer wavelength, and then this is then absorbed by the atmosphere, and this absorption of longer wavelength radiation increases the temperature, which is our global warming. Okay, each one of those points is absolutely essential. Explain how planting trees reduces global warming. Well, this is where our biochemistry comes in, our biology. Well, okay, we can do it two different ways. We'll start with trees because they mention the word trees, okay? So, what do trees do? How do trees link at all? Well, trees use carbon dioxide. And we could say by photosynthesis as well if we want to. Oh yeah, so let's say that, for photosynthesis. They don't just sort of use it for a bit of fun, they use it for photosynthesis. Why is that important? How does that reduce global warming? Well, CO2, or carbon dioxide, causes global warming. Okay, so you could sort of put that at the top or at the bottom in reality, but it's all about you showing that you know carbon dioxide causes global warming and trees use. Now, I've used the word use, but you could say absorb carbon dioxide for photosynthesis as well. Okay, lovely long method, big diagram. Okay, with a question that has this much text in it, they're going to ask you about quite a few different aspects of it. Okay, we have 6.1. The equation for the decomposition of hydrogen peroxide is, describe a test. Lots of tests in this test. Okay, so we have test for the gas produced. Well, it is essential that you know that H2O is water and that tends to be as a liquid, and O2 tends to be as a gas. So our test for oxygen is a glowing splint, and it's important we say the condition of that splint. It's glowing and it relights. So there's not a huge amount of writing in this to get the marks, but you have to know both aspects. So using 10 centimeters cubed of hydrogen peroxide solution gives less accurate results than using 20 centimeters of hydrogen peroxide solution. Well, less accurate, right? That's the crucial bit, less accurate results, okay? What are we looking for if it's less accurate? We're looking for something that is going to not be the correct value. So why would using 10% be less good than 20%? Well, what is the main difference between them? It's going to produce a smaller volume of gas. I mean, that is actually what is going to happen if we have 10%. Okay, now why is that smaller volume of gas going to cause the results to be less accurate? Well, the smaller the volume of gas, the smaller the measurement we make, the easier it is to make in error, and the greater percentage in error this is going to be. So if we read 9 centimeters, it's going to be a bit harder than if we're reading 19.5 centimeters. It's going to be less accurate if we're using very small measurements. So the error in our reading is going to be larger. Okay, and not just larger, it's not going to be a bigger number, so it's not larger in that sense, it's larger as a percentage of the total volume. So if I say it's 10 instead of 9, it's a decent percent, that's 10% of the value. But if I say it's 19 instead of 20, that's straight away a smaller percentage, it's 5% instead of 10%. So the error in reading is considerably larger as a percentage if we're using smaller numbers. Okay, again, said this is the method used. So they give you this method, and then it says one possible source, so that's that, of systematic error. So this is a question all about errors. Systematic error. Well, systematic is something that happens every single time. It's not because you did one mistake along the way. It is something that is happening every single time you do the practical. So it's not, or rather, steps 5, 6, and 7 are going to be affected by it just as much as everything else. Okay, but what is happening above steps 5, 6, and 7? Well, we're measuring the temperature every 30 seconds using a stopwatch. That could be something that is wrong. So our timer, our stopwatch, could actually be fast or slow. When we push the button, it might not immediately stop. So straight away, all of our times are going to be wrong. That's one of our systematic errors. It could be too fast, it could be too slow. Okay, what else? Well, we're also measuring, so that's our time. That could be wrong. It could also be our mass. It could also be our volume. Okay. Now, the way we answer this is going to be very similar. So if we said the mass balance, okay, what could be wrong about the mass balance? We know from a zero error, it's always a little bit higher, but we might not have seen that and recognize it as a zero error. It could be badly calibrated. So it might not be that actually it's showing a zero error. It might start at 0, but it's actually badly calibrated. Okay, now again, that's our mass balance, but we could also say the measuring cylinder is the same. And we think of this less obviously because there's lines drawn onto it, but it could be the same. They could have painted the lines on the wrong bit, etched the lines into the wrong actual volume, so they might all be incorrect or badly calibrated. And all of these things of the equipment being wrong is our systematic error. Okay, we then have this, we need to plot a graph. Okay, now if you look, it is 3 marks for this question. Plot the data from table 3, draw a line of best fit. Okay, there's only 3 marks for this, which means it's going to be 2 marks for plotting the data and 1 mark for drawing a line of best fit. So you need to be really careful with your data when you're plotting it. Okay, so they've said the first line has been plotted, first point I should say has been plotted, which is perfect because that's our 0, 0. We then have 30 seconds and 22, so that takes us up to here. Okay, we then have 60 seconds, and that takes us to 38, so that's here. We're looking at the line, thinking that's a pretty nice line we can draw. We then have 90 seconds, and that is 41. That's looking like a curve. Then we have 120 seconds, and that's 54. Now, I'm looking at this thinking, that looks weird. That looks like there might be an anomaly in there. I'll carry on just to check. We then have 150, it's 58, and 180 is 60. Now, it's really important. Plotting the data gets you 2 marks, so I think it looks
strange. That third value, that third cross looks odd. So if I go back to my 90, measure it again, 41, that is right, I have plotted it correctly, which means it must be an anomaly. So they're drawing a line of best fit, they're looking for me to ignore that anomaly along the way. And that's really important, because if I draw a line through that anomaly, it's wrong. Automatically that line of best fit is wrong. Okay, which catalyst gives the fastest rate of reaction? Okay, so we have this wonderful catalyst. How are we going to know which gives? It says use the completed figure 3, okay? So if we go back, we can have a look that there are 3 different graphs, and we can see the manganese, spell it, the manganese, always gets confused with magnesium sometimes. Manganese dioxide gives the fastest rate of reaction as a catalyst because it has the steepest gradient, and that is the line we have just drawn. It's the steepest, so it's going to be give the fastest rate of reaction. Now the next one, the rate of reaction is not dependent on the volume of hydrogen peroxide solution. Okay, if we look back at the question, that is telling us the volume is not going to change. It's going to be the same, but also it's going to be the same concentration. So if the rate of reaction is not dependent on the same concentration of hydrogen peroxide, why is that? Well, what does same concentration mean? Same concentration means it's the same number of particles per unit volume. Okay, a little bit like density in some ways, the same number of particles per unit volume. And why does having the same concentration mean anything? Well, it's the same number of particles. That means it's going to have the same frequency of collisions. And that's really important, knowing that concentration is all about the number of particles per unit volume, and therefore the frequency of collisions. Our last question. Figure 4 shows the results. Determine the rate of reaction. Now it says at 20 seconds. It's really important. Show you're working on figure 4. Also really important. That means you're going to get a mark for drawing something on this graph. And then give your answer to 3 significant figures. It's worth 5 marks. It's worth a lot of marks, which means there's lots of things we need to get in there. So if it is at a specific time that we are working the rate of reaction, that means we need to draw a tangent. Okay, tangents are fun at the best of times. Okay, so the way I would do it is I would get a ruler, I would get to my 20 seconds mark, okay, and I would draw a ruler line up to the 15, draw a ruler line down to the 5, and the only reason why I would do that is it's going to make my calculations considerably easier. Okay, so what do I have? Well, my rate of reaction is the change in y over the change in x. Still works for my tangent, but now I've got more solid lines. So my change in y is going to be, my rate is 15 centimeters cubed, take away 5 centimeters cubed. That's so much easier to do. And then my next one I can look at, well, the x-axis, it is going to be going through here, which is 32, 34. That's going to be 36. And I'm going to be taking away 2 and 4. I'm going to be taking away 4. Okay, so how am I getting these marks? Well, I've drawn my tangent on. That's going to get me 1 mark. I'm then showing how I'm working out the rate. I've got my y and my change in x. And then I'm going to say my rate is 15 take away 5 is 10. And then I'm going to say 36 take away 4 is 32. Okay, then I'm going to get my calculator out. And I get my calculator out, and I say, what is 10 divided by 32? And this is where it becomes important, because we start thinking, right, we're looking at 3 significant figures here. So 10 divided by 32, it's a lovely number. I think every time you draw a tangent, it looks slightly different, so you need to make sure you've got the right one. So that is my rate. that's not 3 significant figures, so I need to round it. If I get to this far, I will get 4 marks. I have to round it to 3 significant figures, so it's going to be 0.3, 1, 2, and 3 to get all the marks.